So I will frame it as a lemma. I will frame it as a lemma, and look what the lemma says. It says, if I have a set of n vectors, v1 up to vn, and if I know that this set is linearly dependent, if I know that, it's something which actually this slide is hugely inspired by my previous example. But now I'm trying to present you a formal approach to what we just discovered back then. And I strongly recommend you keep that example in your heads right now, or if you can just split your notes and keep it next to you, it will be another good thing to do. Look at this. So if I have such a setting, it's a setting of the previous example, but now it's a general consideration which works not only for n tuples, but for polynomials, functions, any other linear spaces we have. Then I say that we can always find a vector within the set. This symbol, remember, it treats exists. There's always a vector within the set such that this vector can be solved in terms of the other, the way we did with the vectors on the previous slide. There is always a vector which can be solved in terms of the other. Look, I'm going to write this in symbols now. Vector being a vector is can be solved in terms of the others. What I say in symbols is this. Look at this. The same sentence, vector can be solved in terms of the others. In symbols, I write like this. Vector vk, this vector which can be solved for, is in the span of a smaller set, S1, where S1 is my original set S, from which I remove the vector vk. This line, or these two writings, they just say the same thing which I said verbally. Vk is a vector which can be solved for in terms of the other. It's the first statement of my lemma. The second part of my lemma says, in fact, if you take the span of this S, it will be identical to the span of this smaller set from which Vk is removed. So in fact, in terms of taking a span of a set of vectors, removing vector doesn't really change anything. So you can take actually the smaller set without losing anything, which is a good thing. Smaller set, less computations. Let's just look at the proof. So because we assume that my set of vectors is linearly dependent, so I know that we have a scalars. Here they are, from my field of scalars, lambda 1, lambda 2, lambda n, such that if I take linear combination of my vectors, that will be 0. I'm just interpreting here the definition of linear dependence. And the other thing we have in the definition is that not every element in this sequence, lambda 1, lambda 2, lambda n, is 0. Okay? This is my interpretation of the set of vectors being linearly dependent, a just expansion of this assumption of my lemma. Okay, so since I'm saying not everyone is 0, there is one there which is non-zero, right? There is one there, but let's just say it is this lambda k, one of them, lambda k is non-zero. In fact, I'm going to say just for the sake of this presentation, I will assume that the first one is non-zero. Because the setting is symmetric, it doesn't matter which one you're assuming is non-zero. My assumption will be, just for the sake to make the presentation simpler, that the first one, lambda 1, exactly the first one, is non-zero. Sometimes in the books they put this WLOG in front, which reads this without loss of generality. You can make this extra assumption. So WLOG, can I write this? Without loss of generality. That's the expansion for this abbreviation. So if I make such an assumption, here's my solution. If I make an assumption that lambda 1 is non-zero, then I can solve this thing for v1. Why can I do that? But because I can divide by lambda 1. Because if I make the assumption lambda 1 is non-zero, I can divide by that coefficient. Unless I know for sure the coefficient is non-zero, I cannot cancel that. But if I know it is, I can cancel that. So I can solve this for v1. And that will be the end of this story. Because if I solve for V1, here's my solution. If I solve the whole thing for V1, here's my solution. Coefficient next to V2 will be negative lambda 2 by lambda 1. Coefficient next to V3 vector will be negative lambda 3 on lambda 1. And every time the number in the denominator is non-zero number. Many other coefficients like so. The last one will be negative lambda n on lambda 1 times Vn. And that's obviously in the span of the S1, right? Because this is a linear combination of the vectors V2, V3, and Vn, where S1 is my original set. It's the set of the vectors like in the original one, but without V1. You see, V1 is missing in S1. And that's my that's the solution. That's the proof for the first part of this lemma. It's very close to my solution to the example, actually, almost line by line. It's just the difference is that here I give you this formal symbolic representation for those arguments, and it's something you have to learn as well, how to take the example and formalize the ideas from that example in the general argument. Here's the formalization. Okay, let's do the second part of the lemma. Let's do the second part of the lemma, which says that if the span of the sets of this larger set and a smaller one will be identical to each other. Let's just do it like this. So I'll take a vector from my span S1. So I'll take a vector from the right-hand side here. We all know what it means being in a span. Being in a span means that the vector admits the linear combination representation, like so. You see, I changed the names for the coefficients because I want to fix these lambdas, like so. So it means that we have a sequence of coefficients, and we need only n take one of those coefficients, mu2, mu3, and mu_n, all of them from my number field, such that my x is equal to this combination. If I now complete this or extend this representation with one extra vector, with the vector v1, with the trivial coefficient 0, like this. So if I add one extra term here, 0 times v1, this thing will be in the span of the larger set, S, right? Because now v1 is also involved. And so what we see, look at this, I started with the vector x in the span of S1, and I concluded that such a vector will also be in a span S, meaning that every element from here will be in here. Or in the mathematical language, it says span of S1 is a subset of a span of S. And that's, so we just show with you the embedding this way or inclusion this way. Now, the second part of the proof will be showing the embedding this way, the opposite way. Let's just see that. For that, I will start with the vector in S this time, in the left-hand side. We all know what it means to be in a span. It means that my vector admits the linear representation, or representation is a linear combination. All of the n vectors involved this time, you see, v1, v2, vn, all of them involved. Mu's are my coefficients from the vector field. From the number field. Now, what I can do is this. I can take this v1, and I can use what we established in the part 1, that v1 is solvable in terms of v2, v3, vn. So I can basically take my v1 and replace with the right-hand side here. Here it is. mu1, and here's the replacement for my v1 vector. Here's the whole solution taken from here. The rest of this expression I just copied. The rest of this expression is just copied. Here it is. So if I now rearrange the terms, because if you look through this expression, you see that only vectors from v2 up to vn are involved. So if I rearrange the terms now, here's my rearrangement. The coefficient next to v2 will be of this type, right? mu2 from here, and negative this large one from here. And many other coefficients like so. The last one will be the coefficient from here, mu_n, and this one times with this mu1 is my Vn, and that is the element of span S1, you see, because only vectors from V2 to up to Vn are involved. So the second line, it shows me that span of S is a subset. We took any element from the span of S, and we show that this element lands in the span of S1. So it means that the span of S is a subset of a span of S1. And that's how you formally justify the identities between sets. You have to show that one set is a subset of the other set, and vice versa. The second set is a subset of the first one. That's exactly what I did just now in front of you with the quite detailed exposition, actually. These two together, they let me conclude that the span will be like so. Any questions? Right. Now, this lemma actually admits the development, because look what happened. We had a set of vectors which was linearly dependent, and due to this lemma, we were able to drop one element from that set. And without affecting how much things we can span with the set, right? What happens if my new set, S1, is also linearly dependent? Well, I can repeat the step, right? I can drop another vector. Again, without affecting how much things I can span with that. So it will be my new set S2 from which another vector is gone. And if this new set S2 is also linearly dependent, I can again reduce it by one vector. So I can keep reducing this set without altering how much things I can span, as long as we have linearly dependent vectors. As soon as we hit the set which is no longer linearly dependent, which is linearly independent, I can no longer do any reductions. That's another thing which we observed in my previous example. Remember, there was vector v4, which we drop, v3, which we drop, and only v1 and v2 stayed, which are linearly dependent. And basing on this lemma, I can claim now that whichever vector I can span with the v1, v2, v3, v4 from the previous slide, I can also span that vector with the v1 and v2 alone. That's something which I call a corollary at the bottom of this slide. Here's my formalization for the corollary. If I have a set of vectors in V, don't look at this end yet. Then I can find a smaller set, which I call S dash, such that the span of my smaller set is the same as the span of the original set, and at the same time, this smaller set is linearly independent. Here's a corollary, which I just voice it for you, and which is a corollary of my lemma. Do you believe in that corollary? There's one exception to this argument. One flaw in this argument. What if I never hit the linearly independent set? Could that happen? It could happen. It could happen if all of my vectors v1, v2, vn are zero vectors. I never said they're non-zero, and I never said they're different, pairwise different. Did I say that? I didn't. If all of them zero vectors, you will be able to solve one in terms of the other. It's a very trivial solution. You will be dropping the vectors without affecting the span, and the span of this set of zero vectors, no matter how much zero vectors you throw in that set, it will be just a zero subspace. It's still legit. It's a case which I have to exclude from my corollary. Here it is. This only works when the span of the original set is non-zero subspace. Because if my original set spans a zero subspace, meaning that every vector in the set is a zero vector, we will never reach the non-zero linearly independent subset there.